Okay, good morning. Sorry, I zoned out there trying to read about odds ratios. Okay, so couple of quick announcements. Sorry, this email just came in regarding one of the announcements. Okay, so the first big announcement in terms of this class is that we will be returning to in-person instruction after reading week. Okay, so that would mean for us on next week is reading week. So March 1st, it's kind of cool. On March 1st, we will have class in person. On March 2nd, we will have lab in person. And on March 3rd, we will have class in person again. So this course was scheduled as an online course as a face-to-face class, not a hybrid class. So we are returning to face-to-face on March 1st. At that point, I am no longer able to stream or record lecture. So this Thursday will actually be the last online/recorded lecture that we have this semester, and the remainder of the semester will be in person, and the lab and the lecture rooms have already been assigned to us. So we will just be meeting on campus after reading week for the rest of the semester, which is about a month, right? So I think we finish on April 6th. That means that our second term test, which is going to be on, I'm going to clarify this right now, but I believe it is March 3rd. March 10th. Okay, actually that's better. So our second term test, which is on March 10th, will then be in person in class. And that also means that the presentations, I don't think, oh, they're in the outline. So the presentations for this class will also be April 5th. Okay, that's obviously not correct. That should be April 9th. Okay, just gonna make sure that I have that correct. So we start in person on March 1st. The last day of class, April 5th. Oh, I see what I'm doing wrong here. Yeah, April 5th. Okay, so this date is correct. So that means that we'll also be able to have our presentations in class on April 5th, which is great. So we can do those in person as opposed to on Zoom. And that will give us pretty much exactly a month, 1, 2, 3, 4, 5 weeks of in-person instruction, including a test and the lab exam, which will take place in lab. Okay, so basically we're meeting back in person on March 1st for the remainder of the semester. I mean, obviously that's pending no changes to instruction delivery mode. If there's any changes, of course, I'll keep you posted as soon as I'm made aware of them. But I'll send out an announcement clarifying this point. But again, as of March 1st, we're back in person. I cannot record or stream any in-person lectures. So if you miss a lecture, you miss a lecture. This is the traditional way of the education system before COVID, I suppose, which we can, I mean, it's a whole other discussion on the merits of recording and whatnot. But anyways, the point is March 1, we will be back in class and the room is CC 5102, and that's going to be inside PeopleSoft. All right, so that's the first major announcement. The second announcement, I wouldn't necessarily describe it as major announcement, is that I have posted assignment number 3. So assignment 2 was due on Friday. I finished writing up assignment 3. It took me a while to put it together. I was trying to be very thorough. I'll come back to this question in a bit in regards to being thorough. So it's a fairly large assignment mark-wise. It's a fairly long assignment part-wise, but it's not really that long. Like, as you'll see when I kind of walk you through it here, what I've tried to do with this assignment is really emphasize the step-by-step process that I want you to take when you're using these models. So a lot of these questions are really small questions that are asking you to do 1 or 2 steps, but it's just to emphasize how you would go about actually working through or how you could use these models in an analysis type setting. And what I'm trying to do here is give you a general outline of a process you could take when fitting these models, because this is what you're going to have to do on your own on the project. So I'm trying to, again, kind of walk you through how you could go about working with these different models. There's no right or wrong way to do it necessarily. And the process can be specific to the type of question you are trying to ask. But again, with this assignment, I'm kind of trying to give you an idea of how you could go about fitting and comparing different styles of models. Okay, so with that being said, this is due March 11th, so still quite a bit of time to finish this. It's not due for almost a month, which is probably helpful. And it is, let's see, 5 total questions. So the questions range from inference about a GLM. So in the first problem, we have a Pareto distribution. This is a fairly traditional, or should be a fairly familiar question in terms of what we've done in the class so far. So you have show that this thing is exponential, write it in canonical form, give the log likelihood function, derive the MLE, derive the information function. We've actually seen examples like this on assignment number 2. So we did similar style problems for the gamma distribution. Remember that when you're doing these questions, when you have distributions that are in, or when you have a random variable that's in exponential form, you don't need to use the definition of the likelihood and the definition of the information function to get those quantities. You can do it that way, but we drove the log likelihood function and the score function and the information function for the exponential, the general exponential family random variable. So you can use those results. And that is what you will see on assignment number 2. If you review the solutions, is that I directly just use those results to compute the functions that I need. All right, now here we're building the walled statistic in question 1. So these first 4 parts are very familiar, but we're going to use them to build the walled statistic about theta. Then we're going to derive an approximate 95% interval about theta given the walled statistic. Remember that if you take the square root of the walled statistic, it's standard normal. So that is included in lecture set number 4, I believe, on inference. So you'll need to review that if you don't remember that property. And then part G is an R question. So you're going to be generating Pareto random variables using its relationship with the normal, or with the standard uniform. So to generate standard uniform random variables, you can just use the RUnif function. And then you're going to calculate an estimate of theta given that sample. You're going to repeat that process 20 times. So you're going to have 20 different samples of size 1,000. You're going to build an interval for each, and then you're going to comment on the bounds of each of those different intervals. All right. Question number 2. Question number 2. Okay. Question number 2 is worth 52 marks, and it is composed of Q different parts, which is kind of ridiculous. But again, the reason for this is to try and walk you through a strategy for evaluating a binomial GLM. So we're working with this aflatoxin data set. The goal of this particular project is to evaluate the effect of the aflatoxin on tumor growth. In particular, I believe it's liver tumors in lab animals. So these aflatoxins are being fed to the lab animals at different dosages, and researchers are recording the number of tumors that appear on the animals. So a somewhat sad description, but this is what the data set represents. And starting from the beginning, we're really just working through model formulation through inference here. So part A, create a scatter plot of the proportion against the dosage level. Part B, propose a GLM. So we want to model the proportion of tumors that we want to model the presence of tumors versus the dosage level. So you're being asked to propose a GLM in part 2, model formulation, give the response variable, the explanatory variable, and the form of the model, but you give it in terms of G of pi hat. So you don't have to give a link function here. Like you don't have to say like log pi hat equals this. You can just write G of pi hat equals the following. Part C, you're going to actually fit the model in R, and you're asked to return 2 values. Okay, so you don't necessarily have to give the R output. You're being asked to return specific values here, in particular the BIC and the log likelihood that was used to calculate the AIC that is reported by R. Okay, so that's worth 3 marks, 1 for fitting, 1 for each of the results. This is in particular, and you're fitting a logistic regression model here. In part D, you're using that output to calculate an estimate of the ED50 and then interpreting this value. In part E, you are repeating part C for the probit model. Okay, so you're refitting and recalculating those 2 values. And then in part F, you're repeating this for the complementary log-log model. Okay, so we're fitting all 3 of the binomial GLMs to this data set. Then you are asked to evaluate fit based off the BIC. And then you're going to be taken through a range of testing procedures. Okay, so for the model selected in G, so the best fitting model according to BIC, does the deviance give evidence that the full model or that the maximum model is required? In part I, does the C statistic give evidence that the fitted model is required? And then you're going to be asked to compare these results. Part K, you're going to be asked to compute the dispersion parameter and then use this to assess over dispersion. We're going to talk about that today in lecture, and I'll show you how to do this tomorrow in lab. In part L, you're going to be asked to scale based off of the dispersion parameter, regardless of whether or not there's evidence of over dispersion. Part L, you're going to be asked to evaluate the output from part M, you're being asked to evaluate the output from part L in terms of the coefficients and their associated Z-scores and p-values. Part N, you're being asked to compare the results from these 2 tests with the results from part M. So you can see there's a lot of different comparison of the output that's taking place for these GLMs. And this is just to give you a sense of what could be contradictions and what could be agreement that can help you to further assess the model. Okay, and then in part O, we're actually going to be fitting the model, superimposing and fitting the model in R, and then using this to evaluate the fit. Part P, you're being asked to produce 2 types of residual plots and comment on those. And then in part Q, a final recommendation. So based off of all the work you've done above, would you actually recommend this model to the researchers? And again, the point is, while the question does have a lot of parts and is quite long, these are not big questions, and you're just being walked through that whole model fitting process from part 1 to part 4, and really emphasizing interpretation of the model and fit of the model, and in the end making a conclusion that would be hopefully useful to the researchers based off of what you have actually studied. Okay, part L, here's a typo, that should be Wisconsin, not Wisconsin. Okay, part 3 is another binomial GLM question, but in this case, we're using it for a different type of problem. So this question is meant to emphasize something we didn't talk about directly in class or lab, but we can easily do using what we have learned in class and lab. And that is to fit a logistic regression model to a multivariate data set where you have more than 1 explanatory value. The goal of this particular study is classification. So we are going to be using our logistic regression model to determine whether or not an observation has a malignant or a benign tumor. Okay, so this variable class, which is associated with the data set WBCA, it has a 0 or a 1 status where, well, I can check. I don't remember off the top of my head which one is which. I believe 1 is malignant. No, 1 is benign. So 0 is malignant, 1 is benign. And you are being asked to classify the observation, use this model to classify the observations based off of, sorry, to predict the classification of each observation based off of a number of measurements of the associated tumor. Okay, so we're going to fit the logistic regression model given the other 9 variables, and then you're being asked to report the residual deviance and associated degrees of freedom. It's pretty straightforward. Part B, you're being asked to compute that pseudo R² measure we discussed in lecture on Thursday. Part C, you're being asked to comment on the usefulness of the deviance given that the outcome is binary. Part D, you're performing backward elimination using the step function. This is something that we have seen in the past, way back in lecture set number 1. And the expectation here is that performing backward elimination is something that you're familiar with. So we're not going to spend, we haven't spent time talking about this directly, but this question is valuable because it'll show you that you can still run these types of processes on your fitted GLMs, and that can be useful to you going into the project. Recompute the pseudo R² for the best fitted model. Comment on the agreement or disagreement between the AICs of the 2 models versus the pseudo R² of the 2 models. So do they agree in terms of the recommended model? And then in G, you will actually be using this model. So in G, we are saying a tumor is classified as benign if pi hat is greater than 0, and malignant if pi hat is less than 0. So given this new observation, or with this particular observation here be classified as malignant or benign using the fitted model from part D. In part 2 of G, you are going to build a confidence interval for part I. That should be a G. I'll update that after. And then in part 3, we're going to perform part I for every observation in the data set and then compute the number of misclassifications based off of this model. Okay, and then questions 4 and question 5 are related to lecture set 7, which we will finish before the end of the week. So you'll be able to complete the entire assignment by the end of this week, or at least start and work through all of it if you'd like. So part 4 is just a little proof asking about the relationship between this nominal logistic regression model. Again, we'll talk about this today. So showing how this relates to a logistic regression model for binary data. And then in part question 5, we're actually going to go through the process of fitting a nominal logistic regression model, which is an extension of the logistic regression model to the situation where your response variable has more than 2 categories. Okay, and that's the focus of lecture set 7. And again, in this question, you're basically just being walked through a model fitting process. There's some interpretation involved and essentially just evaluation of the model as you work through the problem. Okay, so that's assignment number 3, due March 11th. So lots of time to get this done. We have covered all the material for question 1, all the material for question 2. You could do question 3 now without too much difficulty. Oh, actually, we need to do the deviance thing. So by the end of the day tomorrow, you can finish question 2. And then questions 4 and 5 are lecture set 7, which we will finish by the end of the week. Okay, so I will fix up those typos after and repost it. Does anyone have any questions? Okie dokie. So I'm going to stop this. Okay. And then here we go. All right, can you guys see the slides now? Okay, cool. All right, so you can see first off, I've crossed out a lot of things on the slide. Sorry, one sec here. So I've crossed out a bunch of things on the slides. That's because I had little p's in place of the pi's. So all the little p's should be pi's, which is what's happening here. Okay, so we're actually going to start with the over and under dispersion subject right off the start. So this is what we need for lectures for question number 2 on assignment 3. And again, I'll show you how to actually use what we will define as the dispersion parameter tomorrow. And it's very straightforward in R. So this is not by any means a taxing process. Okay, so the idea is basically going back to the start of this discussion. So we've learned how to fit, or throughout this lecture set, we've been focused on evaluating a logistic regression model, which is a one type of binomial GLM. The processes that we've used for the logistic regression model will be analogous or the same as the processes we use to evaluate the probit model and the complementary log-log model. So there's no, in terms of what we have been studying in this lecture set, we can just apply those same principles to those other two models. We have one of the main tools that we've used to evaluate the fit of our GLM is the deviance measure. And we have basically talked about what the residual deviance from R, or the deviance as we have mainly studied it does, is test the hypothesis that the fitted model is sufficient versus the alternative that maximal model is required. So we've been working with hypothesis tests where lack of evidence against the null would be, I guess, in some sense preferred, because that indicates that the model you fitted is sufficient compared to that maximal model. Now, I've mentioned sort of, I guess, sparsely, like on a couple of different points, I've sort of said, oh, by the way, like, okay, so the deviance is giving us no evidence to suggest we need the maximal model, but we actually want the deviance to be close to the degrees of freedom. So when the deviance is too large, this could actually be an indication that the fitted model is not is not a great fit for the particular data set. And in particular, it could mean that, for example, some of the assumptions on the response variable are not holding. And it could also mean, for example, that the data contain outliers, the data could be sparse, there could be clusters of observations within the data set. And it could also mean that the variance of the response is not equal to the theoretical variance, which would be n times pi hat times n times pi times 1 minus pi. Okay, so this is what being over dispersed or under dispersed could mean. So if we have a deviance measure that's too large relative to the degrees of freedom, or too small compared to the degrees of freedom, this could be evidence of over dispersion or under dispersion. We define over dispersion as being a situation where the variance of the response exceeds its theoretical variance, and under dispersion as being the opposite. And again, there's a variety of reasons why this can occur. Okay, some of which are highlighted on slide 24. Okay, so as I had just mentioned, and following up on that, over dispersion can be caused by a number of different situations. So for example, dependence between trials. So that's a violation of one of the assumptions of the binomial distribution. There could be clusters of observations, etc. Okay, so to theoretically define this problem, we can work through the following illustration. So suppose that we have a sample of size n, within that sample of size n, there are L clusters of size k. Okay, so that just means that we have n observations, and there's just groups of the n observations, little L groups of size k. So k plus k1 plus k2 plus k3 plus kl is going to be equal to little n, right? K1 plus 2 plus kl is equal to little n. Okay, so let the number of successes in each cluster called Zi be distributed binomial k pi l. Okay, so each cluster has its own probability of success and its own set of observations. Suppose that the pi l is a random variable such that its expected value is equal to pi and its variance is equal to tau squared times pi times 1 minus pi. Let the total number of successes be y, which is equal to the sum of the number of successes from each cluster. Then the expected value of y is equal to n pi, which is what you would expect. So that's fine. Right? Okay, so however, the variance of y, which is going to be the sum across the variance of each zi, is going to be equal to the sum of the expected value of the variance of z given pi plus the variance of the expected value of z given pi, which is equal to 1 plus k minus 1 tau squared times n pi 1 minus pi. Okay, so this is over dispersed because this quantity here is greater than or equal to 1. Okay, so a fairly simple illustration. So in the context of clusters of data, this is why you would have a variance that exceeds the expected result, which should be n pi 1 minus pi. Right. Okay, so to detect over dispersion, and I think you could also use this for under dispersion, but we're mainly commenting in the context of over dispersion. We can introduce the dispersion parameter psi, sorry. In the standard case, so when the model fits well, this value is going to be equal to 1. So we can estimate phi, and I got to check to make sure I'm not saying phi when I should be saying psi. It's phi. Okay. Yeah, because psi is the trident. Okay, so we can estimate phi using x squared over n minus p, right? Where x squared over n minus p, this is the Pearson chi-square. So basically in R, what we're going to do is just estimate this quantity, which is very easy to do for a binomial GLM. We just compute the Pearson x square value, and then we divide by n minus p. Okay, so if this quantity is greater than 1, we have evidence of over dispersion. Okay, so if psi is greater than 1, we have evidence of over dispersion. All right. If we have evidence of over dispersion, what we do is we scale the information matrix for the model parameters, which in practical terms means that we change the standard errors that are associated with the model parameters. Okay, and we basically just adjust them by multiplying this quantity by phi. And again, we can do this in R very easily using the summary command. Further, if we want to compare two models, so a subset model and a larger model, we also scale the F statistic that we use for that comparison by phi. And of course, this is only really going to apply when this can be an approximate F value in the situation that the deviances are approximately chi-squared. Anyways, the point is that we would also scale our F value for comparing two models by phi as well. Okay, so then this is the situation where we would compare, a subset model and a larger model. Okay, so that's basically all we need to know for how overdispersion works. And again, the crux of it is overdispersion refers to the case where the variance of the observed response is greater than the expected variance under the binomial assumption. To evaluate for over dispersion, we compute this dispersion parameter phi. And then if phi is greater than 1, we can say there's evidence of over dispersion, and then we can adjust our fitted model's standard errors, which would also adjust the associated Z scores, which would also adjust the associated P values using R. And we're going to go over how to do this in lab tomorrow. Again, very straightforward approach. All right. Any questions before I move on? I actually think we have x squared right here. So, I mean, we could do this very easily right now. Might as well just. We have x squared for this model, 10.029. And the degree of freedom, there's 2 model parameters. I can't remember, I think there were 6. Observations. One, 2, 3, 4, 5, 6, 7, 8. Okay. So we have 10.029 divided by 6. 1.6715. Not bad. Right. So this would be but that's actually pretty good. I mean, you're probably never going to observe numbers exactly equal to 1, but the adjustment from 1.6715 is not going to be drastic compared to the adjustment if the dispersion parameter was something like 2 or 3, right? But that would essentially be how we go about computing it. Just the ratio of the chi-square or the Pearson x square statistic to the degree of freedom for the fitted model. Okay. Just want to make sure I got. Okay, cool. Okay. All right. So just a quick example there of how to compute that parameter. Okay. Returning back to the Beetle mortality data, the last thing I want to talk about in this lecture set is model comparison across the 3 binomial GLMs. So we have introduced a fairly large number of different values that we can use to evaluate the fitted model. So for example, we talked about the pseudo R squared value, the R squared value, the AIC, the BIC, the deviance measure, and the Pearson x squared value. All right. So for that Beetle mortality data that we have been using to illustrate the majority of these different measurements, I have fitted the logistic model or the probit and the complementary log-log model, and I have computed these same values for those two models. All right, so in this table, we have a summary of all this different output. So for example, we have the intercepts for the three models, we have the slopes for the three models. There's not much that we can do in terms of comparison between those models. Those certainly aren't going to indicate whether or not one model is fitting better than another model. But it is interesting to note that the complementary log-log model and the probit model both have a beta 1 value that are more similar than the beta 1 for the logistic model. And this is the same with the intercept. So in terms of magnitude, they are closer to one another than they are to the logistic. So the logistic seems to be, in terms of structure, quite different from the other two. But again, this doesn't really indicate anything about the fit. Okay, we have the log likelihood values. We could technically compare the log likelihood values. So these are maximized values on the same data set with the same model structure and only a different link function. Okay, so we can see that the best or the highest log likelihood value is the one that belongs to the complementary log-log model, which would mean that this has a slightly higher likelihood value for the data set of interest given its associated MLE. And that might imply that this fit is slightly better. However, when we're comparing these different values, it's best to use the AIC and the BIC, the adjusted criteria. However, actually, in this situation, the AIC and the BIC are going to have the exact same adjustment across all three models. So the log likelihood, the AIC and the BIC should agree. Okay, so in this situation, because the models have the same number of parameters and it's the same data set with the same number of observations, the adjustments to the AIC and the BIC will just mimic what the log likelihoods are already showing us. So using the AIC and the BIC to compare the models is actually only really going to make a difference when we are changing the number of parameters that are in the fitted models. Nonetheless, we have all three statistics here, and you can see in all three cases that the log likelihood, the AIC, and the BIC are suggesting that the complementary log-log model fits best. All right, now it's important to keep in mind here that this is a maximized value. Okay, so here, let me write this again. So this is a maximized value. Okay, so higher is better. Okay, now with the AIC and the BIC, these are -2 times the log likelihood of pi hat given y plus a penalty. Okay, I'm just going to write plus penalty. Okay. Now, in this situation, again, what we're multiplying by 2. So we have taken a function that's increasing and we flipped it upside down. Okay. And then we've added a penalty to it. So in this situation, it's the smaller value that's actually better. So smaller is better. All right. So you can see if we compare, I'll just highlight the best fitting one. So based off the log likelihood, and then again, the AIC and the BIC are going to agree because P and N is not changing here. Okay, so these are also selecting the best fitting model. Or these are also selecting the complementary log-log model as the best. All right, now, if we look at the pseudo R squared, so you'll recall that the pseudo R squared actually gets larger as you add parameters in. So that's a hint for question 3 on the assignment. But you can see here that given our traditional definition of the R squared value, these are also suggesting the complementary log-log, because again, these are the largest quantities. Okay, so we have consistency across these 5 comparisons, or these 5 tools that are built for model comparison. Okay. So I'm not going to highlight this because I assume everyone knows how to use the R squared value at this point. Okay, the deviance and the x squared. So we actually know that the distribution of the x squared is going to mimic that of the deviance. The two values are essentially equivalent. Now, what's interesting in this situation, so if we focus on the deviance, for example. Okay, so the deviance tests so in this situation, you could technically make an argument that the smaller the deviance, a smaller deviance value gives more evidence that the fitted model is sufficient, because a smaller deviance value is going to result in a larger p-value. And the larger the p-value, the more likely it is that the situation described by the null hypothesis, or the larger the p-value, the less evidence there is to suggest that the alternative might be, I don't want to use the word true. The larger the p-value, the less evidence to suggest the alternative, essentially is what I'm trying to say. So if we look at the deviance here, okay, we could say smaller deviance gives suggest HA. Right. So by that logic, if you want to take that sort of approach or look at it, you can see here that, again, the deviance associated with the complementary log-log is quite a bit smaller than the deviances associated with the logistic and the probit model. Now, in this situation, if we were to compute that dispersion parameter, we would be able to see, based off the x squared, that there's probably a little bit of evidence of under dispersion here, since we would have 3.29 over 6, which is almost a half. So maybe the model is slightly under dispersed, so not a perfect fit, but again, you're not going to expect perfect fits in any applied situation. All right, and then the last value we have is the chi-square. The chi, or the x squared value. So the x squared value has the same asymptotic distribution as the deviance, so it would give the same suggestion. So we could say here, right? So we have, at least in this illustration, we do have consistency across the criteria that we have established for comparing the models, right? Now, a lot of them are really doing the same thing. So you could also argue it's redundant to use all of them, right? Like the AIC and the BIC are essentially the same thing. It's just the BIC has a stricter penalty. given that the number of parameters and the number of observations for these models are identical, you don't even really need to consider the AIC and the BIC. You could just compare the log likelihood values. The AIC and BIC are really valuable when you're comparing models with different number of parameters to one another. That's when they're most useful. And then the pseudo R-squared values, obviously the larger values both correspond to the complementary log-log. The pseudo R-squared is appropriate here, given that these models have the same number of parameters. We did have a note that that value is going to increase as the number of parameters increases. And then the R-squared value, similar idea. So given that the models have the same number of parameters, this is still useful. And then we just talked about deviance in the X-squared. So you could, I suppose, even the deviance isn't really meant to be a model comparison criteria. But again, you could maybe argue that a smaller deviance is giving less evidence to suggest the alternative is required, which could be considered in some sense evidence of a better fit. Perhaps that argument would hold up, but we have the other values anyways for comparison's sake. Okay, any questions? Okay, so on slide 29, I'm essentially just summarizing some of the points that we've already made, or that I made on the previous slide. So basically just indicating how we could use these measurements to evaluate fit. Keeping in mind AIC and BIC are going to give the same results as the log likelihood in this situation. It's just that we're looking for small values because we multiply by -2. Evaluating the R-squared. For the complementary log-log model, we could say there's evidence of under dispersion because that 5 value is going to be less than 1. And then again, a comment on the deviance, basically saying it gives the most evidence to suggest or it gives the least amount of evidence to suggest the maximum model is required because of how small the deviance is. Though the deviance, again, isn't really a model comparison tool like the other values are. Okay, the other thing that we can do to compare the models is actually evaluate them on how they fit the data set. And this is very useful, especially in the context of GLMs, because for example, when you're working with a binary logistic regression model, so one where the response variable is actually a Bernoulli, those distributional assumptions on the deviance don't hold. So you can't actually use the deviance in those situations to evaluate model fit. So what can you do if you want to try and evaluate how well your model is fitting the data in those situations? Well, in terms of the criteria that we've established, the AIC and BIC would still be useful to you because you're evaluating based off of the log likelihood quantity. But the other thing you can do is actually just evaluate in terms of how well these models work for prediction. So in this table on slide 30, I'm giving the observed number of successes for the Beetle mortality data, which if I'm recalling correctly, is the number of deaths of the beetles at the different dosage levels. And then in each of the subsequent columns, I'm giving the predicted number of deaths for the fitted models. So you can see from a raw comparison of the values here, the complementary log-log model appears to have the values that are closest to the observed quantities. So for example, 5.59 is closest to 6, 11.28 closest to 13, 20.95 closest to 18, 30.36 closest to 28. Not as strong at 52, not as strong at 53, not as strong at 61, and then it returns to being the best fit at 60. So it seems like what that complementary log-log model is doing better than the other two is capturing the tail behavior of the observed data set. Whereas the probit and logistic model seem to be better sort of in that middle part, mean area of the data set. Okay, so we could also use this evaluation to try and suggest which model might be the best. And then we can also superimpose the data to study how the lines actually fit the observed data set. So on this plot here, I have my logistic model in black, solid line. I have the probit model in blue dashed line, and I have the complementary log-log in red, different dash type of line. Okay, so from here, you can see that complementary log-log model, again, all three models visually on this slide appear to fit pretty well. We can talk about an approach for evaluating how accurate these values or how similar these values actually are in lab. But you can see that the complementary log-log model, again, you can tell that it's fitting, it seems to be fitting that tail area better, whereas the probit and the logistic model both appear to be underestimating the observed proportion or underestimating the proportion of successes in the tails, but appear to be a bit stronger in the middle part of the data set. It seems like the probit and C-log-log are very similar, and they kind of run more naturally through the middle of the points, those 3 points in the center, whereas the complementary log-log looks like it's biased towards the smaller values, essentially. Okay, so this would be, in all other situations, another way that we could evaluate the fit. Basically, how close are the estimates to the values that are actually given in the data set? So how close are the estimates to the observed quantities? All right. Okay, so then on slide 32, just sort of emphasizing what we could say based off of the previous illustrations, which are that the complementary log-log appears to give the best estimates overall, though the probit and the logistics seem to be a little bit better in the middle part of the data set. If you consider the estimated quantities in conjunction with the model selection criteria that we discussed before, I think that the conclusion here would be that the C-log-log model fits quite well. All right, so that brings us to the end of lecture set number 6. So lecture sets 5 and 6 are about fitting binomial GLMs and evaluating and comparing the different binomial GLMs. We focused on the logistic regression model in terms of theoretical demonstration, application of the model fitting procedure in R, so direct model fitting using the logistic model. And then we also discussed how we could compare using all of the different criteria that we developed in lecture set 6. And then we concluded with just a summary of how we can, again, compare the 3 different binomial GLMs, all 3 of which can be fit very easily in R. And we'll go through a quick example of this tomorrow in lab. Right. We'll also talk about computing that dispersion parameter and how we can use it to adjust the summary statistics, or in particular, the standard errors and the Z-scores for the model coefficients. Again, this is quite easy to do. And then I'll also kind of just run through the computation of these different measures so that you have examples of those. Okay, so that brings us to the end of lecture set 6. So now we can move into the 7th lecture set. So this is going to be a model. We're going to talk about extensions of the logistic regression model now to situations where you have more than two categories in the response variable. So there's 2 models that we're going to focus on. In lecture set 7, we'll talk about the nominal logistic regression model. And in lecture set 8, we'll talk about the ordinal logistic regression model, where the major differences are just that the nominal model doesn't assume order to the categories of the response, and the ordinal model would assume that there is an underlying order to the categories of the response. Okay. So to start off, we're going to define the distribution of the response variable that would be assumed if you were going to fit this type of logistic regression model. Then we will talk about the nominal logistic regression model and how we can interpret that value. And then we'll look at that through an applied illustration. And then we will also see examples tomorrow of how we can fit this in R. Again, not a little bit trickier than fitting a logistic regression model, because if you don't define if you have a specific reference level that you want to use for the categories, you have to define that directly, or R might not automatically use them. So that's something we'll have to talk about. But outside of that, it's done in a fairly similar way to fitting any other linear model, just a different package and a different function to actually call it. All right. So when are we going to use this model? So we want to use this model when we have a response variable that has more than 2 levels in the category. So you want to predict where a particular observation is going to fall among 3 or more categories. Okay, so there's a couple of different ways that we can do this. We can do it through an extension of the logistic model, which is what we're going to talk about today, or through the log link and the Poisson GLM, which is what we'll start talking about after the reading week. Okay, so again, for the nominal logistic model, our response variable falls into 3 or more different categories. In this particular situation, we would assume that the categories don't have a natural order, whereas the ordinal model would assume that there is an order to the categories. The illustration that we're going to look at in this particular data set actually would have an intrinsic order, but we're going to ignore it for illustrative purposes, and then we'll return to it when we demonstrate the ordinal model. The nominal logistic regression model yields what is called an odds ratio. So the logistic regression model gave us the log odds, or the odds of a particular event directly. This is going to give us the ratio of the odds of, or of the odds of the presence of an event over the absence of an event. So this is not the same thing as the odds. It's a ratio of 2 different odds from 2 different events. So we'll talk more about that in a little bit, and I'll define the odds ratio explicitly. Interpreting the odds ratio is not that straightforward of a process. Like, it is essentially a ratio of 2 different odds, but what you could actually say that means is not, it doesn't have as nice an interpretation as, say, like the relative risk, where you're comparing the probability of 2 events. And then you can say this is more likely than the other one. It doesn't have that same overall interpretability, which is kind of a drag, but you do get out a defined value from the model, which is cool. All right. So when we are using a nominal logistic regression model, essentially the assumption is that the response variable belongs to what is called the multinomial distribution. Okay, so the multinomial distribution has density given in equation 1. So the idea is, say that y is a random variable with j different outcomes, or j different categories, okay, such that the probability that the variable belongs to the category j is equal to pi j, such that all the pi j's have to sum to 1. So this is basically saying, if you have one observation that can belong to one of 3 categories, there's a 1/3 probability it belongs to each category. If you have one observation that had to belong to 4 categories, there'd be a 1/4 probability it belongs to the 4 categories. Okay, if there is, or there could be a 1/4 probability it belongs to the 4 categories. Technically, you could have, say, if you had 3 categories, you could be like 0.2, 0.4, 0.4. It doesn't have to be an even probability for each category. They just have to sum to 1. All right. Okay, so given yj outcomes in the random vector y equals y1 to yj, we would write that the sum across all j is equal to little n. All right, so that would be defined such that there would be y1 outcomes in category 1, y2 outcomes in category j, and y subscript capital J outcomes in category j. Y2 outcomes in category 2, yj outcomes in category j. Okay, so n total observations, y1 plus y2 plus y capital J is equal to n. Pi1 plus pi1, pi2, and pi j represent basically the proportionate observations that belong to each category. Okay, we have the expected value of the yj, the variance and the covariance, some additional properties defined below. And we can show that if capital J is equal to 2, then equation 1 should reduce to the PDF for a binomial distribution. Okay, so the binomial random variable is a special case of the multinomial random variable when there's only two outcomes. All right, so we know that if we want to formulate this in the context of a GLM, the response variable has to belong to the exponential family, and it has to be in canonical form. So a multinomial random variable does not directly belong to the exponential family of distributions. But what we can do is express the multinomial through the joint distribution of a Poisson random variable. And we know that the Poisson does belong to the exponential family in canonical form. Okay, so through this representation, we can formulate a generalized linear model about the multinomial random variable. And to do that, we would basically write, or we would consider the following. Okay, so let y1 to y j. Oh, sorry. Let y1 plus y2 plus yj equal to little n. Okay. Then n is distributed Poisson with lambda 1 plus lambda 2 plus lambda j. Okay. Therefore, the PDF for y conditional on little n is f of y given n is equal to the product from j equals 1 to j of lambda j yj e to the negative lambda j over yj factorial divided by lambda 1 plus lambda 2 plus lambda j to the n e to the negative lambda 1 plus lambda j divided by n factorial. Okay. Right. And then we can say that this thing, do I have enough room? No, I'll just write it here. Which simplifies to f of y given n is equal to lambda 1 over the sum n k sorry, over the sum of lambda k y1 times lambda j over the sum lambda k y j n factorial over y1 factorial y j. A little bit more Poisson-like. Okay, so then we can say, or we can show if pi j is equal to lambda j divided by the sum k equals 1 to capital K of lambda k. Then I'll call this 2. Then 2 reduces, or is equivalent to, and the multinomial distribution can be regarded as the joint distribution modeled in a GLM. All right. Okay, so first thing, multinomial distribution, not directly exponential family. We can model it through joint Poisson, and therefore we can say that it can be used in a GLM framework. Okay. Okay, so again, we're going to use the nominal logistic model when the data have no or the categories of the response have no natural ordering. Okay, so we're going to choose one of the categories as a reference category. Okay, in R, depending on the data set, this is going to be done automatically. So if you just load the data in without any other specifications, it'll automatically choose the reference level for you. I'll show you tomorrow how you can set those reference levels. Right, the model itself is shown here. So we have the logit of pi j, which is equal to the log of pi j over pi 1, which is equal to xi transpose j times beta j for j equals 1 to 2. So you effectively have a different model for each of the j categories in the data set of interest. Okay. So this leads to pi j is equal to pi 1 times the exponent of xj transpose bj for j equals 1 to 2. Okay, so we can estimate the probability that an observation belongs to category j using the estimate for pi hat 1 multiplied by exp of xij times bj. It's pretty straightforward calculation. All right. Now to compute those probabilities, we would do the following. So since pi1, the sum of pi1, the sum from pi1 to pi j must equal to 1. We can write that pi1 is equal to 1 over 1 plus the sum from j equals 2 to j of exp xij transpose times bj. And then we can say that pi hat j is going to be the ratio of the corresponding value of x times b exponentiated divided by 1 plus the sum of the remaining values. Okay. So to perform inference about the model, we're going to have the same criteria. So for example, the Pearson chi-square, the deviance, the capital C value. The Pearson chi-square and the deviance are both x squared with p max minus p degrees of freedom in this case. And C is distributed x squared, chi-square, p minus j minus 1. And we'll look at examples of that tomorrow in lab as well. Okay, so in terms of interpretation, I had mentioned before that what we are going to get out of this model is an estimate of the odds ratio. So what is an odds ratio? Okay, suppose that you have some value x, and x can take on values 0 and 1. So 0 is going to be the absence of a factor, and 1 means that the factor is present. The odds ratio for exposure relative to the reference category is given by the following. So it's the probability that the factor is present in the jth category divided by the probability that the factor is absent in the jth category divided by the probability that the factor is present in the first category over the probability the factor is absent in the first category. So basically, it's just a ratio of odds. In this case, from the jth category, the odds of presence in the jth category divided by the odds of presence in the first category. So always with reference to category 1. Right. So when we fit a nominal logistic regression model, what we end up with is the following. Okay, so we have log pi j over pi 1 is equal to beta naught j plus beta 1 j x for j equals 2 to j. All right, so that means that the log of pi j a divided by pi 1a is equal to beta naught j x is equal to 0. And the log of pi j a divided by pi 1a Therefore, the log of the odds ratio for the jth category is equal to the log of pi jp minus pi 1p minus the log pi j a, which is equal to beta 1 j. So the odds ratio for the jth category is equal to the exponent of beta 1 j. All right. Scroll down on that. Okay, so we can directly compute the odds ratio for the present. Well, we can compute the odds ratio comparing the presence of an event in the jth category to the presence of the event in the first category simply by exponentiating the corresponding coefficient. We're going to look at an illustration where we have multiple explanatory values, and we'll talk about how we can adjust our interpretation based off those values. So if beta 1j is equal to 0, that means that the odds ratio is equal to 1. If the odds ratio is equal to 1, it means that the odds of presence are the same in the jth category and the first category, which means that there's no additional effect at that particular in that particular category, right? From this model, we can also get estimates of the probabilities that each observation belong to the different groups of the response variable. So regardless of the reference level, those probabilities will be the same. But depending on how we fit the model, so what we choose as reference levels, the parameter estimates will change. So that would mean that the odds ratios would change depending on which groups you are comparing, which I think makes sense. Okay, so that brings us to the start of the example. It's already 12:18, so I guess I will stop here today. So what I'll do tomorrow in lab then is I'll work through the fitting of the other binomial GLMs, and I'll talk about the computation of those different model evaluation criteria, like the AIC, the BIC, capital C, etc. And then I will show you how to fit the multinomial model, and I'll show you how I fit it for this particular example, but I'll leave interpretation of the outcomes for Thursday so we can work through those together in person. But once you know how to fit the model, it's easy to break down where the different value, where the outputs come from and how to interpret it. Okay, so I'll stop there for today. I'll make a few edits to assignment 3 because I caught a couple of typos, and I will see you guys tomorrow for lab.